Okay, so last time we introduced together how to find the position, velocity, and acceleration in cylindrical coordinates. Now we'll do together some example to practice on this. In the first problem, we have in the amusement park, a chair is rotating in a horizontal circular path of radius r such that arm OB has an angular velocity and angular acceleration. Determine the radial and transverse components of velocity and acceleration of the passenger. So first, in such problem, okay, you can think here in this problem, you can think about two types of coordinate systems, or the normal tangential, and also we'll see that cylindrical coordinates will give us exactly same results. Normally, I told you whenever you have a circular motion, then it will be good to use your NUT. And you will see here that it will be equivalent to your RU theta y in a certain way. And we'll see what is we will compare your RU theta and your NUT in this case. So whenever you consider the circular motion, you can say, let me consider this is the center of my circle. If I want to represent UNUT, UT is tangent to the path. UN is normal directed towards the center of rotation. Now, if I want to consider URU theta frame, what will be the difference? First, if you remember, we defined the radial coordinate unit vector UR as a unit vector directed from the position point or reference point, which is O here, towards the point of interest. So here we are at point B, then UR is directed from O to B. So this is vector UR. And we said that U theta vector, which is the transverse unit vector, is always perpendicular to UR, okay? And we turn from UR in the positive theta direction an angle of 90 degrees. So as you can see in this figure, theta represents the angle between this horizontal reference line and UR, and it's turning in this way. You are turning in this direction. So I should turn also for U theta in the same direction, and this will be my U theta. So if you observe your figure, you will deduce that UT and U theta are the same vectors. However, UN and UR are opposite to each other. This is because of the choice of the reference point, which is the center of the circle. Okay, so now in general, whenever you deal with UR, U theta, you are free to select any point as reference. You can take, for example, this point as reference. If you do it, then UN, UT, and UR, U theta will be completely different. So for example, if they forced you to take this point as origin of your cylindrical frame, you can do it. Then this is my reference line. Angle theta then will present the angle between the reference line and the position vector. And then this is theta. This is my angle theta. And I have that in this case, UT-UN will remain tangent to the path and the normal vector directed towards the center of curvature. However, if I want to represent UR U theta here, let us choose another color. For UR U theta, you have the following. Vector UR, by definition, is directed from the origin of your cylindrical coordinates, if you want, to the point of interest. So this is, UR will be along OB now. So it will be like this. So as you can see, it will be different. It will not be anymore having same direction of UN. So this is UR in this case. And if you want to represent U theta, U theta is perpendicular to UR, turning in the positive direction, an angle of 90 degrees. So this is my U theta. And then because of the new origin I considered, U theta changed completely. Okay. Of course, in circular motion, it's the best choice is to take the center as origin because it will be easier to work with it. Okay. Now, let us try to determine the expressions of velocity and acceleration in cylindrical coordinates. And we'll see together that they will exactly refer back to the equations in U and UT. Okay, so according to their figure, as we said, this is UR and this is U theta. And let us now find the expressions of velocity and acceleration in this frame. I will start with velocity. If you remember last time, we derived together expressions of velocity and acceleration in a radial coordinate system. And we have seen that the velocity vector is given by r dot UR plus r theta dot U theta. Okay, and we said that r dot represents the radial component and r theta dot represents the transverse component of velocity. Okay, now if we want to do the analysis here, what is r in this problem? R represents what? It's the distance from the center, which is O, to the point of interest. Is this distance changing with location? So if I'm taking a new location, will R change in magnitude?
No, so r dot equals to 0.
Exactly. So because I selected the center of my circle as my reference point, then whatever is my location on this circle, the distance between O and this point will not change. It's equal to the radius of the circle. And because of this, then since R is constant in magnitude, equal to the radius of the circle, then R dot is 0. So first I deduce that for this example, I don't have a radial velocity component. I just have this one, which is it's the transverse component. And this is, I can expect this. Why? Because as we said, UT and U theta here are coincident, okay? And then we know that in U and UT, how is the velocity? The velocity is always tangent to the path, so it's along UT, okay? And we know that the expression of velocity vector in U and UT frame is velocity magnitude times UT vector. And if you remember, we said that V represents the linear velocity. And when you have a circular motion, this linear velocity can be related to what? What is theta dot?
Angular velocity.
Yes, very good. Theta dot is the angular velocity. And as expected, we know that linear velocity can be related to angular velocity by r times omega, and omega is d theta by dt. So it's r theta dot. So using cylindrical coordinates, we obtained exactly the same result as in normal tangential coordinates. So this is for velocity. Velocity doesn't have a radial component. It only has a transverse component in this case. Now, what about acceleration? To get the expression of acceleration, let us go back to the formula we derived together last time. What was the expression of the acceleration vector? The acceleration vector, here it's a 2D motion, so no Z component. So we have along UR, R dot
Doctor, بس can I ask you one question?
minus R theta dot square. This is along UR. While along U theta, you have 2r dot theta dot plus r theta dot dot. Don't worry about these formulas. No need to memorize them. I'll give you a formula sheet. Okay. So this is times u theta. Let us apply now in this case. Okay. We already said that for this particular case, r is constant. So r dot and r dot will be equal to what? Both are equal to 0. So we can start to do some simplifications. This term will cancel out. And also this one will cancel out. And we'll end up with two components, the radial one and the transverse one. And let us make the analysis to see how it's exactly giving us the same result as normal tangential coordinates. First, if you remember, we said UR is opposite to UN. This is why we expect that how will be AR? AR will be negative. It's minus r theta dot square, because we know that in circular motion, the normal component is always directed towards the center of rotation of curvature. And we have that here an, which is equal to v square over r, will be expected to be equal to minus r, because UR and UN are opposite. And we can verify this because we know that the linear velocity v can be related to the angular velocity theta dot. So we can replace v by, if you replace v by r theta dot, what do you get? You get, since it's a square, you get r square theta dot square, r squared theta dot square over r. So if you simplify r, you will end up with minus ar equal to r theta dot square. So as expected, ar is minus r theta dot square. Okay. Now, concerning the component along u theta, we said that here u theta and ut are coincident factors. And we know by definition, what is AT? AT is simply the derivative of velocity with respect to time. Okay, the linear velocity. And if we replace the linear velocity by its expression, so we should derive r theta dot with respect to time. And if we do this, we have that since the radius is constant here, we can take it outside of the derivative. And we know that the derivative of theta dot with respect to time is theta dot dot. So AT is equal to r theta dot dot. And this is what we obtained here. Okay. AT is equal to this component, which is a theta. So as expected, we got exactly the same result. Okay, so in this problem, you can see that both normal tangential coordinates and cylindrical coordinates can be used. Now, in which problems it's we will use cylindrical and in which ones we'll use U and UT, it depends on the given. Now we'll do several examples on cylindrical coordinates to see in which case we use them.
Dr. There's one
Yes.
question.
Yes.
In questions, you will tell us the expression of theta and we will derive it
Yes.
with respect to time.
Yeah, exactly.
Or...
Now we'll do an example. We'll do an example on that. Yes. Any other question on this problem before we move to another one? Okay. So now we have several possibilities to work in cylindrical coordinates. The first type of problems you might encounter is that theta angle is provided as a function of time. and R angle is also provided as a function of time. And then in this case, it's very simple if you want just application. And with this problem, we are just starting by an application problem that is simple. We gave us the angle variation with time. We gave us the position magnitude variation with time. And they want us to find the velocity and acceleration of the color when t equals to 1 second. So this is a very typical case. We just have to apply formulas, okay? We start by saying, what is the velocity vector in radial components? Why here I should use cylindrical components? Because it's very clear here, because theta is provided and R is provided function of t. In case, for example, they gave me x, y function of t, then I will use Cartesian coordinates. In case they gave me a curve for which I can calculate the radius of curvature, and they told me the increase in speed is of this amount, then they are telling me use u and ut. Okay, so here all I have to do in this problem is to do direct application of the formula. I have that the velocity is equal to r dot ur plus r theta dot u theta. So in order to compute my velocity, I need to find the expressions of theta dot and r dot. Okay, so now I need to derive. I have that theta is t cube, so theta dot is 3t square, and theta dot dot is the second derivative of theta. It's equal to 6t. I will do the same for r. I will get r dot and r dot dot because I will need them for acceleration. So r dot is 200t and r dot dot is okay. And now I just replace for t equal 1 second. I determine what are theta dot dot, r dot, and r dot dot. And then I can replace in my equation to get the velocity. And I will do the same for the acceleration using the formula that a vector is equal to r dot dot minus r theta dot square along ur and plus r theta dot dot plus 2 r dot theta dot along u theta. So I have everything here. I got all expressions needed for theta dot dot, r dot, and r dot dot. I replace at the times they asked me for. The only challenging issue here is if you want, as I told you before, whenever they ask you for a vector velocity or vector acceleration, never give your final answer as angle. So if you want to get the magnitude and angle, for the magnitude here, it's a 2D application. So for V, it's radical VR square V theta square. The same for A. Now, what about the direction? If you remember last time we said the direction should be always referred to the reference line, not to moving unit vectors. U theta here are moving unit vectors. So at each instant, you have a new positions for your U theta unit vectors, okay? So if you want to get, for example, the angle alpha of the velocity vector, do not give it in terms of the angle it's doing with UR or with U theta. Give it with respect to your reference line. Let us do the analysis here, how to get the angle with the reference line. What is the reference line here? Whenever we work in cylindrical coordinates, the reference line is the one from which we are determining the position of the position vector. So as you can see here, the position vector at B here, so vector OB, which has a unit vector UR, is, so this is the vector position R. The vector position R is doing with the reference line an angle of theta, okay? And in particular for this example, we are interested at t equal 1 second. So if we want to find what is theta at 1 second, all we have to do is to replace here, and please pay attention, it's in radian, okay? So theta is equal to 1 radian. You can keep it in radiant if you want, or you can transform it to degrees. So to transform to degrees your angle, you can just do the following. It's a proportionality rule. You say that pi corresponds to an angle of 180 degrees. If I want to find the angle theta, which corresponds to 1 radian, then I can say that theta 1 second is equal to 180 over pi. Okay. And now, once I find the angle between the reference line and UR, I can say, let me find the angle between the reference line and the velocity vector. We said that the velocity vector has two components, and we found these components, okay? From your calculation, you were able to calculate VR and V theta. So let us see what were the values and how we can make the analysis for the angle it's doing with the reference line. So after performing our calculations, we obtain the following. We obtain that we have VR positive and V theta positive. So value of VR is 200 millimeter. Value of V theta is 300 millimeter both per second. And then we can now find what is the angle between V and UR. So to get, let us call this angle delta here. Okay. So we can say that delta is tan minus 1 of, if we look at our figures, this side, which is V theta over VR. So it's tan minus 1 VR over V theta. Here, no need to take the absolute value because they are already both positive. Okay, so this will give you 2 over 3. If you do the ratio, it's tan minus 1 of 3 over 2. Okay, so it's equal to tan minus 1 of 1.5.
دكتور مش في
sorry بالعكس يا بالعكس V theta over VR. Yeah, V theta over VR, so it's tan minus 1 of 3 over 2, which is 1.5. Okay, and then you can get your angle theta, delta. Now, after you get delta, if you go back to your figure here, okay, if you go back to your figure, then what is the total angle between the reference line and V? What should you do then? Look, we can illustrate it here so you can see it better. This is the velocity vector. This is a vector perpendicular to V. Okay, you already found the angle theta here is pi over, we said, we did the rule. Okay, so it was equal to, if you calculated, it is 57.3. It's 180 over pi, which will be equal to 57.3 degrees. And now you calculated the angle between UR and your velocity vector, which you named delta. So in total, the angle between the reference line and your velocity vector is theta plus delta. Okay, so at this position, you have just to add these two angles to get the direction of your velocity vector. Any question on how we found the direction of V?
As I was Dr. lastly,
Yeah.
what do we need to add لنطلع velocity vector إنه الدايركشن تبعه؟
Okay, we need to add these two angles because already, if you remember, we first calculated theta at 1 second. Theta represents the angle between the reference line and your vector UR, your position vector. Okay, and it was found to be equal to 180 over pi. Okay. Now, since you don't want to express velocity just as its direction with UR, you want to express it relative to the reference line, then you should find this angle, this whole angle. So if I illustrate it in another color, you should find between the reference line and the velocity. This is why you should add to this angle theta, which is between the reference line and UR, the angle between UR and V, which is delta. So in total, the angle between V and the reference line will be theta plus delta. Okay?
Okay.
Let me check your chats if you have any questions in the chats. Hashim, it's fine. Okay. Now, let us
is there a way
consider.
to change UR U theta to IJ and start working?
Yeah, look, you can. It's here in this case. It's easier instead of putting IJ frame. It's easier to work with the reference lines I gave you. No
Yes.
need to put a new frame IJ. Okay. You can do it. You can put. You can say I want to consider this is my I. Let's say, and this is my J vector. And I want to express in this frame. You can do it, but no need. You just have to give the angle with a fixed reference line, which is this one. Okay?
Yes.
Now, we'll do the same job for the acceleration. Okay? So if we replace r dot dot, theta dot, theta dot dot, and theta dot or dot by their values we found at 1 second, we can obtain the expression of acceleration within frame UR U theta. And as you can see, you have a negative UR component and a positive U theta component. Always, this will help you to determine the quadrant of your vector. So in plane UR U theta, this is my UR vector. And this is my U theta vector. In this frame, I am in the second quadrant because I have a negative value of AR. Since AR is negative, it's directed towards point O. Okay. And since my A theta is positive, so it's along the positive direction. So this is my A theta. Now, once I determine A theta and AR, okay, and I represent, if you want, my position vector, which is my acceleration vector, which is here, then I can say, let me find the easiest angle. The angle here will be between negative UR. So I choose the angle lower than 90 degrees. I will represent the angle between negative UR and A. Okay. This angle, we'll call it phi. So because this angle is smaller than 90, when I do 10 minus 1, I will take the absolute value here because I determined the quadrant, and now I just take the angle that is smaller than 90 with the closest axis, which is here minus UR. So tangent minus 1 here, I should do absolute value of A theta over AR. And then I can say that phi, so this is phi, this is the angle I want to calculate. So phi is equal to tangent minus 1 of A theta here is 1,800 and AR is minus 700. But since I'm interested in the absolute value, I will just take 18 over 7. So this will allow me to calculate my angle phi. Now, the next step, okay, will be to refer back to the reference line. So as I told you, always at the end, when you want to find the angle, give it with respect to the reference line. So this one. if I look at my figure, then I should represent this total angle. Okay, this one. And this angle is equal to the angle between this line and this one, which is equal to what? This is theta. So it's 57.3. Now, what should I add to this angle? What should I add to it? Which part? This one. This angle is equal to what here? Between positive UR and A, what is the angle?
180 minus phi.
Exactly. So this part, I know that this is phi. This is phi. So this part will be 180 minus phi. So in total, my angle is 180 minus phi plus 57.3. So my acceleration vector is doing an angle of 169 degrees with the reference line. Okay. And of course, for the magnitude, all I have to do is radical AR square plus A theta square. Any question on this? Okay, let us do another problem.
Doctor,
Yes?
why did we do the absolute value?
We did the absolute value because we specified that we are in the second quadrant. So now we are not looking at the angle with positive UR, okay? If you take the angle with positive UR, you will not take the absolute value. You should take them as they are, yani one positive, one negative. But as I told you last time in class, when you have a calculator and you do tan minus 1, let's say, of theta component over UR component or Y over X, you have two solutions. Yeah, the first quadrant and the third quadrant will give you the same value of tan. And if you have, for example, this line, you can say the angle, it depends on your vector. If your vector is in the first quadrant, you will select the solution smaller than 90. If you are in the third quadrant and you just put the sign as they are, okay, then you should give the angle this angle, this small one, plus 180. So in general, in order to not always have to think which angle should I give, I just select the angle, the quadrant first. Yani I select my quadrant. I say I know I am in the second quadrant, so no need to give the angle with positive UR, which is larger than 90. I can just calculate the angle which is smaller than 90, which is this one, which is the angle with minus UR. And since I'm sure that this angle is smaller than 90, then tangent minus 1 will be positive, will be of a positive number. So I take the absolute value of A theta over AR. Okay.
Just can you repeat why it's less than 90?
It's less than 90 because now you determined your quadrant. إذا أنت بقلب quadrant فحيعمل هول السميشن of these two angle is 90 صح؟ فأنت عم بتاخد angle أصغر من 90 أكيد هو أصغر. يعني if I give you نعم.
تفضل.
Yes.
Yeah, I was saying انه طب اذا ما عملنا الابسوليوت مش بناخذ الانجل الكبيره بنبطل بدنا نعملها 180 minus
اذا ما عملت الابسوليوت الابسوليوت فاليو بس تعمل A theta over AR حيطلع لك نيجاتيف فاليو. اوكي هلا هيدي النيجاتيف فاليو بالكالكوليتر فيها تعطيك دغري فاليو هاير ذان 90 degrees، بس بيرجع انت مفروض بالاخر تقرر اذا انا بالسكند كوادرنت او بالفورس 1 لانه بتفرق. اوكي يعني انت اذا بالفورس كوادرنت بدك تعطيني الانجل هيدا كله، فتمام يعني بكل الاحوال you should determine in which quadrant you are. This is why to avoid this confusion from beginning you say I'm in which quadrant. Let's say I am in the second one. خلص بجيب الانجل الاصغر يلي دغري مع minus UR بدل ما اجيب الانجل مع positive UR.
Thank you.
اوكي هلا at the end you can do whatever you want. ما في one يعني هون مثلا ساعتها بدل ما تعطيني 68.7 اذا بدك تعطيني اياه مع positive UR بدك تقول لي الكالكوليتر اوريدي الكالكوليتر تعرف شو حتعطيك فيها تعطيك الفاليو مع بتعطيك نيجاتيف انجل وانت يعني لانه الفورث كوادرنت والسكند كوادرنت نفس اللاين يعني هي حتعطيك هيدا الانجل الكالكوليتر حتعطيك -5 اللي هو -68.7 هيك حتعطيك الكالكوليتر بس انت لازم تعرف انه انا ماني بالفورث كوادرنت تاخذ النيجاتيف انجل انا بالسكند كوادرنت يعني what I should do هو I should say that this angle is 180 يعني بدي زيد plus 180 okay يعني 180 minus 68.7 So in order to not go over all of these issues, you just determine what is your quadrant. And once you know your quadrant, you just find the angle مع الأقرب axis يعني إذا بدك أو UR أو minus UR هون أو plus U theta هي Z. ساعتها بتاخذ tangent minus 1 of the absolute value لأنه الأنجل هون أكيد أصغر من 90 degrees. Okay. Any other question on this? Okay. So let us do another problem. This is a little bit more challenging, okay? In this problem, you have to write the equation of your motion, and then you will do your derivatives to get velocity and acceleration. The searchlight casts a spot of light along the face of a wall that is located 100 meters from the searchlight. Determine the magnitudes of the velocity and acceleration at which the spot appears to travel across the wall at the instant theta is equal to 45 degrees. The searchlight is rotating at a constant rate of 4 radians per second. So in this problem, they gave me that the rotating rate is constant equal to 4 radians per second. So what is the variable they gave me here?
Angular velocity.
Yes, yes, they gave me omega or theta dot. So this is an indication. This is an indication that I have information in cylindrical coordinates. So I will try to profit from this information and try to write what is r function of theta and then derive to get my velocity and acceleration. Here I should do the relation, and in general I use a geometrical relation to be able to relate r and theta. Okay, so we'll try to find out in this figure